So we have a leaky cylinder. The farmer has just filled his tank 4 metres high and 4 metres in diameter. So there's our tank. 4, radius is 2, and it's got a hole in it. Water's definitely leaking out, and it sort of makes sense that if the water's really high, there's going to be a lot of pressure, so there's going to be a lot of water coming out. If the water's low, not much pressure, not much water leaking out. So we've got the hole. The water leaks out at a rate that is proportional to the height, which sort of makes sense. 10 hours later, the water height is just 1 metre. And then days later, we're going to try and fill the tank. So there'll be water going in and water going out, and we've got to fill the tank. Anyway, so let's think about this in 2 stages. The first thing is to work out stage 1. It's leaking. So we're told the rate at which it's going out is proportional to the height. So as water leaks out, the height decreases. So I guess I can say dH dt equals kH. Let's get the H and the dH together and the K and the dt together. Integrate kt plus c. We're pretty good at this now. Now it was full. H equals 4 when t equals 0. It was full at t equals 0, so clearly we're going to get this H equals 4 e to the kt. And then 10 hours later, the height was just 1. 10 hours later, the height was just 1. So 10k equals the natural log of 1/4. K equals that on 10. Let's just put, there we go. So even though I can now go H equals 4 e to the natural log of 0.25 on 10 t, that function isn't really what we're chasing. Don't really care about that. What do I care about? I've got this constant that feeds back into this statement that the height's going to change proportionally, the rate of change of height will change proportionally with the height of the water. So that K is really, really important. That's really all we were chasing in that first section. Now let's think about the water going in. So again, we've got our tank. So I've got a dV dt, and it's 20. I'm filling it at 20 cubic metres per hour. So our volume's going up at 20 per hour. And really I need something to do with the height. It's all about the height, isn't it? Because this is all about height. Height equals. So I've got to have a dH dt. And eventually I'm going to have a H equals, and I'm going to set H equal to 4 to get an answer. Okay, so dH dt. We could probably do this without a differential equation, but where's the fun in that? So dV dt we're missing a dV dH because I've got dV dt is 20. I want this dH dt, so I'm missing. Now here my R is 2, So that's going to be, r squared is going to be 4. So 4 pi h, so dv dh will just be 4 pi. So dv dh is 4 pi. So dh dt will be 5 on pi. I guess if you think that would be meters per hour. So every hour my height is going to go up by 5 on pi. Clearly ignoring the fact that there's a leak. Just sorry to delay the video, but just think about that. R is 2, so I've got 4 pi h, and I'm pumping in at 20 meters per hour. So that means if my hour was 1, it would be... So that's the way you get that without the differential equation, is just thinking about in 1 hour, how high does my cylinder go? Well, if I've got to fit 20 cubic meters in there and I've got a radius of 4, my height's got to be 5 pi. But again, we're big boys and girls, let's use the differential equation like we just did. Okay, so let's again go back to this highlighter. So we've got a dh dt is 5 pi, and I've also got a dh dt, is kh. They both are happening when we're talking about filling the tank, because that's emptying the tank and that's filling the tank. So we can get a brand new dh dt is actually a combination of filling the tank plus our kh. Our k, we know our k, but I don't really want to put the natural log of 0.25 on 10 and have that carry through. It would be really nasty on the algebra. So I'm just going to leave it as k, but I know k is not an unknown. I know what k is. All I really need to do is get a statement that says all I'm chasing is a h of t, and then I'm going to set h equal to 4 to find out how long it takes to fill the thing up. That was the question. How long is it going to take to fill it up? So all I want to do is integrate that. There's a h and a dh, so I want to get them together. So I'm forced to go 1 on kh equals, that would be dh, get the dt on the other side, integrate both sides. Now if we look at our left hand side, we are desperate to get a k up there, therefore we want to put a k on the other side to even be multiplying both sides by k, so we keep it the same. That gets me my pattern of the derivative on top of the function. So now I can just go, well, that's got to be the natural log of kh equals kt plus c. C e to the kt. Remember, we know what k is, that's not a problem, but we don't know what this c is. But we are told, well, wasn't it days later or something that days later when the tank is completely empty, so that's a hint. Days later when the tank is completely empty, that means when t equals 0, h equals 0. So 0 plus e to the 0, well, e to the 0 is 1, so c is 5 on pi. We are nearly out, which is good because I'm out of room. H will equal, I've got to subtract that 5 on pi, and then I've got to divide by k. Now remember, I know what k is. K is the natural log of 0.25 on 10. The natural log of 0.25 on 10. We can ditch that k. This is definitely a tech active situation because we are solving for t. All we need to do is set h equal to 4 because that's the height of the water when the tank is full. We're setting h equals 4 into the function. We're solving for t and we're going to get t equals, I don't know, 3.08986 hours. Oh my gosh, I'm out of paper. There we go. That was fun. It's about separating it into when it's leaking, when it's filling up, and then combining the two together. Awesome question. Love it.